Welcome back to Science Hub and Tech. My name is Femi. Here's a scenario. You have a sequence of rooms. The first room is big. The second room is inside the first one. The third is inside the second. Each one nested inside the last, getting smaller and smaller. They keep shrinking, infinitely many stages, smaller and smaller. Is there a point that's inside all of them? A point that survives every single stage of shrinking? Let's explore this and more after the break. Welcome back. Theorem 3.25, the Cantor Intersection Theorem. Let Q1, Q2, Q3, and so on be a sequence of non-empty closed sets in R such that each Qk plus 1 is contained in Qk and Q1 is bounded. Then the intersection of all of them is closed and non-empty. Non-empty. There's always at least one survivor. At least one point makes it through every stage. Why? Here's the argument. Pick one point from each set. x1 from Q1, x2 from Q2, x3 from Q3, and so on. Now, all of these points live inside Q1 because every Qk is contained in Q1. So we have infinitely many points trapped inside a bounded set. And we know what happens then. Bolzano-Weierstrass. There must be an accumulation point. Call it x. But here's the key step. Why is x actually in every Qk? Pick any Qk. Look at the points we chose. xk, xk plus 1, xk plus 2, and everything after. All of those points are in Qk because Qj is contained in Qk whenever j is greater than or equal to k. So only finitely many of our chosen points, the first k minus one of them, could possibly be outside Qk. But x is an accumulation point. Every ball around x catches infinitely many of our chosen points, and only finitely many of them are outside Qk. So every ball around x must catch at least one point that is in Qk. That means x adheres to Qk, and Qk is closed. Closed sets contain all their adherent or limit points, so x is in Qk. This works for every k. So x is in Q1, Q2, Q3, every single one. X is in the intersection. The intersection is non-empty and closed because the intersection of closed sets is always closed by Theorem 3.13. But both conditions are essential. Both. Let me show you what breaks if you drop either one. First, what if Q1 isn't bounded? Take Qk equals k infinity. These are closed. They're nested, each one inside the last. But Q1 equals 1 infinity. That's unbounded. The walls go on forever. And the intersection? Empty. There's no real number that's bigger than every positive integer. The points drift off to infinity with no wall to stop them. No confinement, no compression, no survivor. Boundedness is not optional. Now, what if the sets aren't closed? Take Qk equals the open interval 0, 1 over k. These are nested, each one inside the last. Q1 equals 0, 1, which is bounded, but they're open, not closed. And the intersection? Also empty. Is there a positive number that's less than 1 over k for every k? No. For any positive number you name, I can find a k large enough to make 1 over k smaller than it. So nothing survives. The problem is that 0, the point that wants to be in the intersection, isn't in any of the sets because they're all open intervals that don't include 0. If they were closed, then 0 would be in every single one, and the intersection would be 0. But openness lets 0 slip through the cracks. Closedness is not optional either. Now we're going to use these tools to answer a completely different kind of question. If you cover a set with open sets, can you always thin the covering down? And how thin can you get it? That's Lindelof and Heine-Borel, coming next. And the Cantor Intersection Theorem we just proved, the entire thing leaned on Bolzano-Weierstrass. If that theorem isn't solid for you yet, watch this video right here. Have a golden day or night ahead.